Welcome back, grade 10s. In today's lesson, we're going to continue learning about electric circuits. In the previous lessons, we have discussed current and we have discussed voltage. Remember that current is the rate of the flow of charge. In other words, current measures how fast are those electrons running through the circuit. Voltage is the energy used per unit charge. So voltage is how much energy is needed to push those electrons so that they can run around the circuit and create a current. Now, an electric circuit that just has electricity running through it is useless. It is only useful if we can run the current through a material or a circuit component known as a resistor. And inside that resistor, we would get that electrical energy to get converted into other forms of energy that are useful for us. So what is resistance? Resistance is defined as the opposition to the flow of current. So when the current, meaning those running electrons, come across a circuit component that makes it hard for them to move through, they are experiencing resistance. If we have an electric circuit without a resistor, then the electrical energy is useless to us. There's absolutely no point to having electricity unless that electricity is passed through a resistor. And what is a resistor? Well, that's a special circuit component that has high resistance, meaning that it opposes that flow of current. And through this opposition to the flow of current, it converts the electrical energy in the moving current into other useful forms of energy. This resistance within the resistor is what is responsible for converting the electrical energy into other energy forms that are useful to us. We need to understand that all resistors are associated with some heat energy conversion. Sometimes in a resistor, we want heat generation, in which case it wouldn't be a wasted energy. But in other cases, in a resistor, when heat is created, we don't actually want or need that heat, in which case it is wasted energy. So for example, in a TV, the electrical energy gets converted into light, sound, and heat energy. Of course, when we're watching TV, the light and the sound energy are useful. But the fact that the TV generates some heat energy, that is wasted energy. And there's nothing we can do about that because, as I already mentioned, all resistors are going to be associated with some heat energy. In a fan, the electrical energy gets converted into mechanical energy, sound energy, and heat energy. Now, what we want to get out of the fan is we want that turning action, and that's mechanical energy, so that's useful. But the fact that the fan creates sound and some heat energy, well, that's wasted energy. And in fact, the sound energy from a fan can actually be a bit of a nuisance, and we're always looking for a fan that produces less noise, so less sound energy. In a kettle, the electrical energy gets converted into heat energy, but there's also some sound energy. Sometimes if a kettle has a little light, then there's also going to be light energy associated with it. Now, in a kettle, the heat energy is useful because we're trying to boil the water. But the sound energy, the sound that the kettle makes, well, that's wasted energy. At a microscopic level or at an atomic level, what actually causes resistance? Well, if you consider a piece of copper wire, so just consider these yellow or brown circles over here. And those represent the copper atoms that make up the copper wire. Now, electricity is made up of free electrons that are moving through the conducting wire like the copper wire. So these little blue dots over here represent the free electrons, which are moving through the conducting wire and creating an electric current. So on a microscopic level, we have free electrons that are moving through the conducting material. And as they're moving through the conducting material, they are going to bump into the atoms, the copper atoms that make up this conducting material. Now, when those electrons, those free electrons, collide with the copper atoms of the conductor, there's going to be some friction, and that results in the formation of heat. So remember that I said that all resistors are associated with some heat, and this is the reason for it. So the electrons are always going to convert some of their electrical energy into heat energy in any resistor. It is also important to note that a conducting wire, although it is an excellent conductor of electricity, still offers some resistance, but that resistance will be very low. So a conducting wire made up of, say, copper, aluminium, silver, gold, platinum, which are excellent conductors of electricity, are still going to have some resistance associated with them. And that's because the conducting wire, whatever material it is made up of atoms. And the electrons that make up the current are going to bump those atoms, and that's going to cause warming up of the conducting wire after some time. And that proves to us that there is some very low resistance in the conducting wire as well. Now, when the electrons encounter a resistor of high resistance, and remember that a resistor is also a conducting material, but it is a bad conductor of electricity, and that creates even more friction between the conducting material of that high resistor and the electrons that make up the current. In a resistor, the friction is going to cause the resistor to heat up fast. Now, depending on the resistor and what we want to use that resistor for, other energy conversions may take place. And of course, that depends on the appliance that we're using and the resistor within that appliance. Let's consider an incandescent light bulb. An incandescent light bulb has got a tungsten filament in it. So it's got a very thin curly wire here made up of tungsten. This is the resistor in the light bulb, and it is surrounded by a glass housing. Now the electricity enters the light bulb through copper wires, and then it has to travel through the tungsten, and then it leaves the light bulb through copper wires again. Now, when it enters the tungsten filament, it is facing very high resistance, and that causes the electrical energy to transfer into heat energy. And that heat energy is so high that it causes this filament here to glow white hot, which then produces light energy. We need to understand that the copper wires that connect the light bulb to the cell or to the mains in the house, those copper wires only warm up slightly because their resistance is low. But the tungsten that is conducting the same amount of current is going to warm up a lot because its resistance is so high. Again, all conducting materials are going to have some resistance associated with them. Good conductors, like copper wires, have low resistance associated with them. And bad conductors, like tungsten, are going to have high resistance associated with them, and hence we use them for different purposes. Lower resistance conductors are used in conducting wires, and higher resistance conductors are used as resistors. Energy-saving light bulbs, instead of using a filament, they use gases. And when current flows through those gases get excited and they produce light. But they produce a lot less heat. So the idea is that with the same amount of energy entering those energy-saving light bulbs, they can produce the same amount of light, but overall they use less electricity because the amount of heat that they release is very, very low. Just to provide you with a visual and keeping in mind that I'm completely making up numbers here. But if I have 100 joules of energy going into my tungsten light bulb, let's say half of that is released as light, 50 joules, and half of that is released as heat. And remember that the heat energy is wasted energy. But if we look at an energy-saving bulb, and we want the same amount of light out of it, so it is producing the same amount of light as the incandescent light bulb. However, it is only wasting 10 joules of electricity as heat energy. So that means that the total input of energy needed is less to get the same amount of light. Let's now discuss the 4 factors that contribute to resistance. The first one is simply the type of material. The type of material impacts the resistance of a material because different materials have their atoms arranged in different ways. They have their free electrons arranged in different ways. And based on that, some materials would be better conductors of electricity than others naturally. The second factor is the length of the material. So if we have 2 resistors made of the exact same material and they're identical in every other way except for the length of the resistor, the longer one will have a higher resistance than the shorter one. And that makes sense because running a 100-meter race is going to be easier than running a 500-meter race. So the longer the resistor, the higher the resistance. The third factor is the thickness of the material. So again, imagine 2 resistors that are identical in every way. They're made of the same material. They're also the same length, but one material is thicker than the other. Now imagine running water through a thick hose pipe and running the same amount of water through a thin hose pipe. It is going to be easier for the water to move through the thicker hose pipe. In the same way, the thicker the resistor, the lower the resistance. And finally, the temperature of the material. Coming back to this diagram, remember that these brown circles are the atoms that make up the conducting wire. Now, whether this is a conducting material or a material with a higher resistance, if those atoms are heated, they are going to vibrate faster in their position. And if they're vibrating faster, what does that mean for these little free electrons that are trying to get through? What's going to be harder for them to get through. And that is why, as the temperature increases, the resistance increases. As temperature increases, these particles are going to vibrate faster. They are going to make it more difficult for the electrons to get through. Hence, there is a higher resistance. So in the case of metals, the higher the temperature of the resistor, the higher the resistance. Now you might recall that this is not the case when it comes to semi-metals or metalloids, where they actually conduct electricity better at higher temperatures. Resistance is the ratio of the voltage and the current through a resistor, and that's defined by Ohm's law, and we're going to learn about Ohm's law in grade 11. But for now, we need to know that resistance is calculated as voltage divided by the current. So V is the voltage measured in volts, and I is the current measured in amperes, and R is the resistance, which is measured in ohms. Now, if you look at this diagram over here, it is very, very helpful. And it's important to come back to this diagram and this little summary here whenever you're confused. So what we can see here is that the current is trying to move through the circuit. So current is the electrons running through the circuit. It is measured in amperes and it is represented by the letter I, which is quite confusing. Then we have the voltage. Voltage is the energy per unit of charge. So it is how much energy is there to push those electrons through the circuit. It is measured in volts and it is represented by the letter V. And finally, the resistance is the thing that makes it harder for the current to move through the circuit. The volt, which gives the energy to the current to move through the circuit, has to work harder when the resistance is higher. So the resistance is how hard is it for the electrons to move through the circuit. It is measured in a unit called ohms, and it is represented by the letter R. Let's now look at some simple examples where we get to apply Ohm's law formula. A 9-volt battery is connected to a circuit and a current of 3 amps flows through the circuit. What is the resistance of the circuit? We know that R equals V over I. So it's 9 volts divided by 3 amps. And that gives us an answer of 3 ohms. Remember that an ohm is actually a volt per amp. An electric iron has a resistance of 20 ohms and is connected to a 240 volt supply. How much current flows through the iron? We may rearrange our formula to get I equals V over R. So it's 240 volts divided by 20 ohms, and that gives us a current of 12 amps. And finally, a resistor of 10 ohms has a current of 0.5 amps flowing through it. What is the voltage across the resistor? Again, we may rearrange the formula as V equals I times R. So it's 0.5 times 10. And we get a voltage across the resistor of 5 volts. That brings us to the end of this lesson. In the next lesson, we are going to focus on series circuits. And in the lesson after that, we are going to focus on parallel circuits. And finally, we will put all the concepts that we've learned together with some past paper questions.